Hello, this is Ethan, and I'm going to be showing you my parallel fractal rendering engine, which I made for Northwestern CS358 final project. So what is a fractal? So you guys may have heard of fractals before, but I think the easiest way to explain them is it's basically an infinitely detailed pattern. So as far as you can zoom in, there's still more detail. So something in nature might be a coastline where the closer you look, the more jagged the coastline is going to get. No matter how much you zoom in, the coastline is always going to get more jagged, right, instead of smooth. Or you could think of snowflakes, where if you keep zooming into the snowflake crystal, it always, might repeat, or there's more detail in the crystal structure. And so those are two examples in nature. But if you look down here, this is probably the most famous example from math, which is the Mandelbrot set. And so this is actually super simple. So if we just break down this image we're looking at, this is basically the complex plane. So if you think over here is like our negative real axis, over here is our positive real axis, negative imaginary axis, positive imaginary axis, and each one of these pixel values represents a complex number in the complex plane. And we basically have an iterative algorithm, and we run this, and depending on how long it takes that specific complex number to diverge to infinity, we color it, right? So for these black pixels, it took very long to diverge. For these lighter pixels, it was very fast, right? And so we're basically iterating we're iterating the formula, and then if it ever exceeds, so if the absolute value ever exceeds 2, then we know it's going to diverge to infinity. We're going to return with how many iterations it took that to happen. And then this is basically just an image coloring how long each coordinate took to escape to infinity, right? So as you can see here, you can also see the command I used, because this was rendered with my engine right here. So next I'm going to show you guys the Julia set. The Julia set is actually very similar to the Mandelbrot set. It actually uses the exact same formula. So with the Mandelbrot set, if we look a little bit closer here, C basically varies for each pixel, right? So whenever I say the pixel is mapped to a certain complex number, that complex number is C. And we're starting with Z not equals 0. So for each one of these, we're doing 0 squared plus C, and then feeding that back into the function, and do that squared plus C again, where C is basically the coordinate of each pixel. For the Julia set, C is actually kept constant for every pixel. Z naught is equal to, where each pixel is in the plane. So Z naught is basically the Mandelbrot's equivalent of C. So they're kind of flip-flopped. And this actually generates an infinitely family of fractals, right? Because with the Mandelbrot set, we were just varying C. Now we vary C, but we can also vary our Z naughts, basically. You get multiple different ones. So we can see this first one rendered with C equals minus 0.8 plus 0.156i, and then this one was rendered with minus 0.8i as C. And you can see they produce completely different images, right? So if you were thinking about rendering this, the first way you might think of doing it is a sequential way, which is, kind of looping through each pixel in the image, mapping that to its complex plane coordinate, running the fractal algorithm, seeing how long it takes to escape, then assigning that pixel a color, move that to the next pixel, and then repeat, basically. Repeat until you've kind of marked every pixel a color, and then you can take that pixel buffer you've set up and convert it to a JPEG. And that's basically exactly what my rendering code does. And you can kind of see it's natural to parallelize this work. All of the work being done is completely independent, right? So it doesn't really matter if we have one thread working on a pixel over here and another thread working on a pixel over here, or anywhere in the plane, because none of the pixels are dependent on each other. So that's what we actually do. But first I want to talk about anti-aliasing, because this kind of clutters the code a little bit. But essentially, instead of taking the mapping from pixel to complex plane and just taking that point, we're also sampling, a dx and dy around that point in order to average it out to get a smoother, crisper image, right? So this is going to take a hit to our performance, because obviously we're doing, in our case, 16 times more work because we're taking 16 samples. But it's always going to be a trade-off, and I think that this trade-off is worth it because you get much nicer images, and that's kind of the point of this fractal renderer, is to make some cool pictures. So if we actually look at the parallel rendering algorithm, it's pretty simple. It's very like our sequential algorithm. The only difference we have is instead of doing all the work pixel by pixel, we are parallelizing it. So we have, up to T threads working at once, all on different pixels. So we can kind of see here. I used OpenMP for this, and we just have one preprocessor directive here, and it's basically saying we want to parallelize this for loop with T number of threads, which is given as a command line argument to the program, and we want a dynamic schedule. What that means is that, for example, if we look at this fractal, if we just naively kind of gave, say, each thread gets a band of the image, some bands are much more compute intensive than others. So this would be an unbalanced load. So what the dynamic schedule does is it helps kind of bounce these loads between threads. So if some threads finish, they can pick up work from other threads. And it makes, we kind of make the most of our hardware, which increases our performance. The last thing we have is collapse, which basically takes these two for loops and combines them into one, which makes it a lot easier for load balancing over the threads. And additionally, we don't have to write another OpenMP inside of here. It's just very clean and it collapses into one, so this parallelizes both for loops. Also, if you guys are looking at the code here, a lot of this junk has to do with just the thread safe RNG. So random number generation actually is not thread safe normally, and I ran into a lot of performance issues there where I was rendering my images and it was taking a really long time, and I discovered it was because I needed a thread safe random function. So if you guys want to learn more about that, I have included a link here. But you can see the code here. Like I said, very similar to the sequential algorithm. We just have an OpenMP compiler directive here, which allows for the, kind of obvious parallelization strategy, which actually improves a lot. So if we look at the results here, we are rendering the exact same Julia set fractal every single time with the same settings. So we see on our first run here with one thread, it took 29 seconds. Two threads, about half that at 15 seconds. Four threads, about half that again, 7.9 seconds. 8 threads took 4.3 seconds. 16 threads took 2.5 seconds. So you can see kind of a linear speed up. One thing to note is that even if I try more threads here, I won't see a real performance gain because my machine only has 16 working cores. If you wanted to have more parallelization, you might look into using MPI, where you have a massive distributed system, or you could look into CUDA. So CUDA is a different way of programming, right? We're used to programming for parallelization on the CPU, but the graphics card is built for these sorts of workloads where all of the data is massively, embarrassingly parallel. In our case, each pixel is completely independent, so each GPU thread can work on a different pixel at once. And the way that this GPU architecture is designed is that you have, maybe 80,000 different CUDA cores that can be working on different pixels at once, whereas on a CPU, you can only have maybe, in my case, 16 threads, 32 maybe if you're lucky, right? Now, one thing to note is that CPU is much faster than the GPU generally, like CPU cores execute many more instructions, but you have this massive layout of cores that, in this case, I think we could see some really true, really good scaling whenever we would put this on a GPU. And I think if I were to continue this project, I'd look to making, a port to work on CUDA, because I would like to test out how does CUDA fare with just our regular OpenMP implementation, and are there any trade-offs? But overall, I think it would actually make the code a lot faster. So thank you guys for listening. I've actually used a Python script to basically generate the frames for these videos and just animations that I used that were rendered by my Fractal rendering engine. So hopefully you guys enjoy this. So the Mandelbrot zoom is, we're just, zooming into the Mandelbrot, and you can see the infinite detail. The Julia sets over here, it's basically varying the C based on, a parameterization of it, and it makes this super cool spiral, and we see, even with all the chaos, we still see these patterns arise, which I think is just so awesome. If you guys want to check out the projects, I put the GitHub up here. You guys can see all the code here, or code there. Yeah, but thank you so much. I really enjoyed the class, and thank you guys for your time.